So, Chapter 4, Electromechanical Systems. So we've got this first portion of the course that covered electronics proper, right? We did a lot of analysis of circuits and learned a lot about different types of electronic components, their use, and different applications. And then we switched gears after the first midterm, and we started talking about systems from the perspective of system dynamics, right? So electronic systems were included, but also beyond that was the state space modeling of, well, electronic and mechanical system domains. And so now we've got electronic domain and mechanical, translational, and rotational domains, and we want to bring them together. And that's what we're going to do in this chapter on electromechanical systems. So lecture 4.1 is on ideal transducers. Two-port system elements can model transducers. So we've been dealing with one-port elements for the most part. We talked about how like an op-amp was 4-port and how MOSFETs were 2 ports, and etc. But for the most part, we've had 1-port elements which have 2 terminals on them. So a 2-port element can model transducers, which are elements that transfer energy between 2 energy domains or change its form within an energy domain. The quintessential example, which will be considered in detail, is the motor, which converts electrical energy to mechanical energy. However, many other system elements can be considered transducers, and we'll consider a few in this lecture. So we're going to talk extensively about motors in the coming lectures, but I want to keep it pretty high level for right now, and we'll do a little motor example, and then we're going to dig into the details starting on Friday of motors. But motors are part of a larger class of systems that we want to introduce today. So each of the 2 ports has a through and an across variable. So you could think of this as being a box with 2 terminals on side 1 and 2 terminals on side 2. And this is the transducer. It has a through and an across variable. So we'll use generalized variables. So this would be the through variable would be F1. And the across variable, drop across these, would be V1. And the through variable into port 2 could be F2 with a drop across the terminals, V2. Okay, so an across variable on each side and a through variable on each side. We use the convention that the power into each port, so the power being P1 into port 1 and P2 into port 2, is positive, which has implications for the signs of the power flow variables F1, V1, F1, F2, and V1 and V2. For a 2-port element to transfer power, we have to have the power into each port summing to 0, right? And we know that power is the product of the power flow variables, right? So P1 is F1, V1, and P2 is F2, V2. Also moving the P2 over to the other side of the equation, we can say that F1 V1 equals negative F2 V2. Okay. Now, we can rearrange this in a couple different ways, and I'm going to do that here, and I'll justify it in a minute, or I'll use the two different forms in a minute. So one way to rearrange this is going to be V1 over V2, which is equal to negative F2 over F1. And the other way you could write it, V1 over F2 equals negative F2 over, equals negative V2 over F1. Okay, so we're going to take these two equations and use them to define something. So we define the transformer ratio, TF, to be V1 over V2. Okay, so this is a little bit weird. We're using two letters to comprise one symbol. And I don't really like this notation, but that's what your textbook uses, the Rowell and Wormley text, so we're going to stick with it. Okay, so TF is one symbol. And it's a ratio of across variables, and given this power argument, this power conservation argument, we know that the ratio of the across variables is equal to the negative ratio of the through variables. Okay. So this first equation gave us that equality here. Now, we could take the other equation and define what's called the gyrator modulus, GY, once again, two letters but one symbol, GY to be the ratio V1 over F2. So from this relationship, we know that's just negative V2 over F1. And so we've defined two different fractions. Really, the reason this one's called a ratio is that you're taking the I guess quotient of two across variables. So there are two things that are alike, right? So we tend to call those ratios. Modulus or moduli in plural, they tend to be quotients of quantities that are dissimilar from each other. Okay, so in this case, we have cross variables and through variables that are mixed in the quotient. So that's why the terminology is a little weird, because in ratios tend to be dimensionless, but if the across variable on one side is voltage and the cross variable on the other side is velocity, then that's not going to be dimensionless when you divide them. So it's a little bit odd, but that is the terminology. As with many things, it's like not super rigorous, but it works okay, so that's the conventions. For an ideal transducer, so an ideal transducer is one that is linear, time invariant, and without power loss, which is already an assumption that we baked into these equations above. We have only two non-trivial solutions. And it's a little bit subtle to go through the description of why there are only two non-trivial solutions. But these are the two possibilities for these equations taken together. This one here, which relates the across variable on one side to the across variable on the other side, and the through variable on side 2 to the across variable, or to the through variable on side 1. So this is called a transformer if this equation is a good model for a given transducer. If this one over here is a good model for your transducer, then we call it a gyrator. And I have made all of the dumb gyrator jokes in the past, so I'm going to skip them today. So the gyrator is different because it relates across variable to through variable, and through variable to across variable. And what we're saying is that one of these two models is going to make a lot more sense for your system. So either this transformer model will make sense for your transducer, or the gyrator will make sense for your transducer. It may not be, in fact, lossless. Like you might have some losses in your motor, for instance. We're talking a lot about losses in a motor and where they come from and how they affect performance. But losses are assumed in these models to be 0. So are we going to have to go back to the drawing board then if we're going to model real systems with these models? No is the answer. I mean, I was kind of tricking you guys. But what we'll do is we'll use these ideal versions. Oh, I froze again. Jesus. We'll use these ideal models, and then we'll take them and augment them with additional D-type elements. So the D-type elements are the ones that are energy dissipative, right? So for instance, a motor has an electronic side and it has coils. We'll talk about what that looks like. But it has coils of wire. And those wires have resistance to them. Okay? So ideally they don't, but when you have a lot of wire wrapped for a large distance, so if you wind it very tightly, you're going to have a lot of wire there. You're going to have resistance. It's going to convert electrical energy into heat. And you can account for that by putting in, on the electrical model side, a resistor. There's not a real resistor there, but we'll put it into our model to model the effect of coil resistance. And on the mechanical side, we're going to have bearing damping. Okay, so we'll use that to model the losses on the mechanical side. So you can use these even for non-ideal situations. You just have to include additional elements. Okay, so that is the idea for transducers. They're either going to be transformers or gyrators, and in these next couple examples we'll take some sort of simple views of that and how we could go about analyzing them. Just a very high level view for now. So let's consider for a moment a DC motor. So DC motors in general, we'll talk in detail about them. But in general, there are these machines that if you run a current through a coil, it induces a magnetic field that turns. So it induces a magnetic field from a static housing position called the stator, and then the shaft is going to rotate on the motor, and the shaft has a so-called rotor on it that gets turned by the stator. So if you have a rotating magnetic field induced by the stator, then the rotor is going to turn as well. And you can, for a DC motor, you can model this very well with a pretty simple relationship between torque and current. And this is a relationship that includes R, which is the rotor radius, the number of coil turns N, the background field B, the rotor length L, and they relate the current through the windings to the torque that's in the shaft of the motor. So the first thing I ask, so we'll talk more about like how these motors work later, but if I'm just giving you this relationship for now. Oh look, I just changed. Now I look like cool guy Greg or something. Okay, so we have to determine if DC motors are transformers or gyrators from this relationship. Now, we look, well, first of all, we identify that current is a through variable, right? And torque, is that a through variable too? Yeah. It's a through variable as well. Angular velocity is the across variable for rotational systems. Yeah?
So for this transformer ratio, we expect it to not have, not be unitless normally, right? It's going to be like 10 volts per meter per second or something like that?
Yeah, exactly. Exactly. So it's not unitless in general. There are cases where it is, and we'll actually consider one of those cases in the second example today. Yeah. So in this case, we have a through variable relating to a through variable, right? So the through variable on the electrical side is current. The through variable on the rotational side, mechanical rotational side, is torque. So our two models, we look at these two models and we see, okay, the transformer model is doing across to across and through to through, right? And the gyrator does across to through and through across, right? So we have an equation that is through to through, right? Through to through is this second transformer equation, right? So we must have a transformer if it matches up with the transformer equation. Okay, so it must be a transformer. Wow, that was big. Transformer. Okay, so we don't need to find the gyrator modulus because it's not a gyrator. We want to find the transformer ratio. If we have a relationship between torque and current, we essentially have we have a relationship between F2 and F1, right? And we can find then what TF is. So we could use this inspection here. It's pretty easy to use inspection here to identify what TF is, but let's actually like algebraically solve for what TF should be, okay? So from one thing I forgot to mention, oh hey, I'm back, is that we call these the elemental equations for a transducer. For a transducer. So notice how there are two, right? So if it's a transformer, there are two. If there's a gyrator, there are two. So the elemental equation for a transformer that relates through variable to through variable. So I can say from the second transformer elemental equation, we know that F2 equals TF, or negative TF. Negative TF F1, which can be easily solved for TF, right? TF is negative F2 over F1 since we are, let's we need to identify which is the side 1 and which is the side 2 here. Let's say the electronic side, it's a motor. We tend to label the one side as being the side where the input comes from, the power side, and side 2 being the load side where the power is flowing to. So assuming that we're using this as a DC motor, the side 1 is going to be the electronic side. Side 2 is going to be the mechanical side. So we can say that F1 is the through variable on the electronic side, or the current, and F2 is going to be the torque. Then we can solve for what TF is, which is negative torque over the current, which is equal to, from this equation, negative 2, just need to divide both sides by I, right? Negative 2 RNBL, and that I we divided over. So the transformer ratio is 2RNBL. Awesome. So we could have done that by inspection too, because this equation looks a lot like this equation. We could just say, oh, T is F2, I is F1, TF is 2RNBL. It's good to go through the exercise once. All right. So 3, derive the relation between the voltage V and the angular velocity omega across the motor, assuming, or using the assumption that it is an ideal transducer. So 3, we've got a relationship between torque and current, and we want to know what the relationship is between the angular velocity and the voltage. Since we know it's a transformer, we know it has to have a relationship between the angular velocity and the voltage, because those are the two across variables here, right? Since we already have TF, we know what that relationship is. Okay? So from the first transformer elemental equation, we know that V2 equals V1 divided by TF, right? So that implies our V2 is the angular velocity, and V1 is the voltage, right? Divided by TF, which, if you wanted to write out the TF in its full glory, is 2RNBL. So that's the analysis of that's first pass at the DC motor. We'll get into more detail later. I decided I'm going to talk about AC motors too. So we might not get to the last bit of the like the last week's material I had planned, I might have to push that to next semester, but I feel like it would be better to just dig deeper into motors while we're here. So we'll see. I have to develop some material for the Friday's lecture before that, so I'll send it out. Okay, gears. So remember I said that transducers typically are converting energy among the domains, but they can also transform it inside a domain as well, and that's what we're going to look at now. So consider two gears with radii R1 and R2 and number of teeth N1 and N2. You'll consider gears in detail in your machine design class next semester, but for now we're just going to look at them from a very high level. Okay. So let's think about, let's say we have I'm going to draw it like that, and then I'm going to draw teeth on it. And it's, say, mating with another gear with its own teeth. So it turns out that number of teeth, the ratio between number of teeth and radii is fixed in gears, which you'll talk all about. But that's why sometimes you talk about number of teeth, sometimes you talk about radii, actually equivalent. You can talk about either one. So let's say that this one's got R1, and this one's got R2. Then first off, let's determine what the power flow variables are for gears. So we're definitely working with rotational mechanical systems when we work with gears, right? I mean, you can have a rack and pinion, which could be a relationship between a rotational and a translational mechanical system. But when they're two conventional gears, those are both rotational, right? And the power in a rotational system, what are the two power flow variables that we've used? We've used torque. So torque on the one side. And what's the other one? Angular velocity. Good. Okay, so torque and angular velocity. Anna is the sneeze police. She's on it. She's on it. Yeah, don't die when you hold in those sneezes. I've heard that it's possible. It's science, man. I actually don't know if that's a real thing, but I feel like it could be.
Well, I know they did like a study where they actually sealed like all the guy's eyes and nose, and he actually had like a stroke.
Jesus. Science. It's science. It's not the science we need, but it's the science we deserve. So okay. And then we've got to have a torque and an angular velocity on the other side, right? So those are the power flow variables for rotational mechanical system for the two sides, for the rotational side on the gear 1 and then on gear 2. So they're presumably rotating on a shaft, right? Each one has its own shaft that's rotating at different speeds in general. Good. So something that we should think about here when we think about gears is, and you're gonna learn a lot more about this, but what is the point of gears? Why do we have gears?
To change velocities.
Yeah, so remember that power is the product of torque and angular velocity, right? So assuming that you don't have a lot of loss of power in this interaction, then the product of torque and angular velocity has to be equal on both sides. If you change the angular velocity from one side to another, which is easily done by changing the radii, right? Then you're going to change, so the power is going to be the same, so the torque will also be different. So if you, for instance, change the speed from what is often you so-called gear down a high-speed motor so that to get a lower speed output, you get more torque, okay? So you get to trade off between torque and angular velocity. And that's a trade-off that we're going to deal a lot with when we're using motors. We have to think about torque, we need to think about angular velocity. These are the two variables that we're most concerned with. So if we've got this trade-off happening, when we look at these two independent equations relating power flow variables, this interaction will become rather interesting. So let's take two different perspectives. Actually, I'm going to go to the next page to get a little bit more space. I'm going to first do a kinematic analysis to relate the angular velocities. So in this kinematic analysis, which one did I draw bigger? Okay, R2. This kinematic analysis, I'm going to have the small one mating with the large one. That was not a great semicircle. We've got our R1 and our R2. And the great thing about gears is that for the most part they don't slip, right? I mean, if they're slipping, you have big problems. Okay, so gears, the idea is they don't slip, right? So at that point of contact, which is actually a sort of imaginary midline intersection that you'll learn about in where it intersects in the gear teeth, a point of contact that happens between the gear teeth, there's no slipping. So you can think of this as being like two cylinders that are have contact at one point that don't slip at that point. Okay? So we'll say assume no slipping. And what do we know about the velocity, the rectilinear velocity at that point then? Or tangential in this case? They're equal, right? The tangential velocity on both of those cylinders is the same at that point. If they're not slipping relative to each other, they can't have a velocity that's different. So we can say that Vt for this smaller gear, for R1, is going to be equal to what function of angular velocity of gear 1? It's something times, whoops, used the wrong omega, omega 1. It's R1, right? R1 omega 1. And you can also say for the other one, you know, it's the same thing. Oh, we need to have a positive direction here, right? Let's do that for positive. So R1 omega 1, good. Vt is going to be R2 omega 2, but the direction of omega has to be the other way, right? So it's negative R2 omega 2. Okay. If you take these together, you can set them equal, right? Vt equals Vt. And you can get a relationship between omega and omega, so omega 2 and omega 1, and it is negative R1 over R2, right? Cool. So this is an elemental equation. It relates an across variable to an across variable. We could identify with the, is it a transformer or is it a gyrator? It's across to across, right? So if we go back up here, you see across to across only happens in a transformer. So it's a transformer. We could go off and do the analysis from here. But we are going to independently do a kinetic analysis to find the relationship between the torques, because you can do that independently too. So let's do a quick kinetic analysis. And the kinetic analysis allows us to look at a free body diagram of each of these. So we have in the interaction, we have a force, an interaction force. I'll call it Ft. And on the other one, it's got to be the opposite direction, right? But equal Ft. Newton had a law about that, right? We like Newton here. Well, actually, he was an asshole, but yeah. So Ft, and we could do a calculation of the torque for of this interaction force for each of these gears. So torque 1 is going to be R1 times Ft, right? It's the force times the moment arm. And it's perpendicular. We're assuming these are nice and circular and all that. And torque 2, is this going to be positive or is it going to be negative R1 or R2 Ft? Is it positive or negative? So remember, we defined this to be positive, and in both cases, the force direction is positive rotation direction. So they're both positive. So we've got Ft in one. So let's solve this one for Ft, for instance. So Ft equals T1 over R1, and let's substitute that into the other equation, which says T2 equals R2. And now we'll bring the R1 over and times T1. So we've related now the torques between the two gears. And we've got this second relationship. So this was our second relationship, the through variable relationship. This is the across variable relationship. The next thing I ask is to determine if the gears are transformers or gyrators, which we already discussed, right? So they're definitely transformers. And in fact, we won't encounter gyrators until next term. I don't think I've got any gyrator examples in this term. So they don't happen in electromechanical systems. At least I can't think of any right now. We can define TF or GY, which we could do from either of these two equations, right? We didn't need them both. We could find TF or GY from either one. So let's use the across variable one, because we used the through variable one before. The across variable elemental equation says that TF is equal to V1 over V2, right? So TF equals V1 over V2, which is equal in this, from this equation. So I'm going to call this star equation. So I'll put this star right here to tell you that's what happened at this equals. Star equation says that omega 1 over omega 2 is equal to negative